Okay. Good morning. It's a pleasure to be here. And by now I feel that me and the prize recipients are friends because we see each other every day. So actually the reason I came here is because over the last several days I heard that we have to invest more money in astronomy. And since everybody tells us the same thing, we have to evaluate the signal to noise ratio. That's basically the ratio between the physics we're going to get and how much money we're going to put. So I came to the colloquium to hear about that. Okay, well, let's have fun. Thank you.
Okay, so we'll have now our talk by Shri.
Okay, I took some liberty with this talk after I realized that there's so many people giving talk on time domain astronomy. And as you heard, if you're all doing one thing, if many of you are doing the same thing, I can't do it. Okay, it's a simple thing, so I thought we'll do something else. I thought I'll talk about the future in the Dan David Prize sense of astronomy, not all of the future, but some part which I've been thinking through. And it may end with a little shock. Okay, so the structure of this talk is, first I'll say, I think the big shifts happening in astronomy, which is worth understanding. Of those shifts, I'll choose only one area which I've thought through a lot, which is the rise of synoptic surveys, of which time domain astronomy is just one. And it's the one that's happening now. Okay. But I think there's something more interesting coming along. It's always the case when you find something, it's happening, which means you already are in it. Always figuring out the future is I find more fascinating, which I would say is the era of bright star astronomy. It's, I predict in a few years, it'll be the big thing. Okay, and maybe the Dan David Prize fellows may want to remember this, the foundation fellows, I mean. Then there's some interesting parts about experimental approaches to astronomy of a different sort. Experimental approach to astronomy came mainly from radio astronomers and then high-energy physicists for CMB investigation and dark energy, but this is a different sort. Beyond that, I think the next one will be a highly multiplex spectroscopy. And then I want to end with the future shock and how we stop getting shocked about it. And for that, I think we should go outside our field. I'll talk a bit about genomics. Okay, so let's understand this paradigm shifts. The old paradigm, and I'll have a slightly more optical perspective, in some sense is reasonable. As some of you know, I did not start in optical astronomy. It's not a biased parochial view, but modern astronomy really, in a big way, begins with optical. From my bedroom and my study window, I can look at the Mount Wilson 60-inch telescope. And I can also look at the 100-inch telescope. It was built, and the least expensive item of that telescope was, in fact, the photographic plate, because that's all was a detector. It was a very low-resolution prism spectrograph or an imager with a lens. And the astronomer was paid already, so inexpensive for guiding. The 60-inch did some pretty amazing stuff, and the 100-inch was almost revolutionary. The expansion of the universe, the first indications of dark matter came from this. And the cost of coming generation, but if you go look at the growth, the coming generations, TMT, EELT, GMT, are approaching space, almost routine space missions at the billion-dollar level. Okay, so the first paradigm shift that's really happened is the cost of general-purpose instruments on optical telescope has risen. We went away from this maybe $10 photographic plate to instruments which can cost as much as $50 million, a single instrument. Okay, MOSFER, Muse, Espresso. I'm sorry, those of you who are not astronomers may not immediately relate to this. Take it from me that these are very expensive instruments. Next, there's been an explosion of what I call as focused projects. That is, there's a theme, usually a grand theme. And right now it is primarily in the early universe with cosmic background radiation and various tests of dark energy, head decks, BOSS, dark energy camera. And then you have in planets, it's slowly coming up, GPI, sphere, and strong gravity. The cost of these instruments is now, some of them, is gone beyond the cost of the telescope, which is a remarkable statement, actually, if you think about it. Okay, so that was my first paradigm shift. The second one is SDSS. We already heard a bit, actually, from Dovey about SDSS. What is this paradigm shift? Well, to me, this is very important. When I started thinking about what to do next, after Swift flew, after 2 years, I said, I'm done with the field because I could see beyond that, things are always exciting and there's huge gain when you launch a mission. And after a while, the growth is linear. That is, you work twice as hard, you get twice as many papers, which is good, but not for me. Anyway, so I started thinking what to do next. And for me, SDSS is a huge paradigm shift. So let me tell you why. It's an amazing survey machine that apparently has the capacity to feed a global workforce. The PhD thesis here in Tel Aviv, Danny has directed. They haven't even gone to the telescope, these students. And they got PhDs, good PhDs, I mean. Okay. And I'm one of these very business-like guys. If I want to understand something, I do quantitative analysis, which I think scientists are supposed to do. SDS has generated more citations per dollar than Keck Observatory, of which I'm a director. It's not something I'm happy, but it's a fact. Okay, then you have to say, why is this the case? Okay, I would say, first of all, a survey can have apparently as much impact as flagship enterprises. Which is true. It's been known in the past. The Palomar Observatory Sky Survey actually had a huge impact, for example. But SDSS had other things. First of all, it took a while for the astronomers to actually understand what we now take for granted. When SDSS was planned, the allocation was $18 million, done the usual way. Mirror, building, road, utilities, whatever. CCD. Okay, that CCD is an instrument. The final cost was $80 million. What is the big difference? It's all in software. I don't mean all 60 million. There's some underestimates. Software now is a part of how we compute our project cost. You put down software as not something you do on the weekend, which used to be the case before. The thing that I found remarkable was, and Avishai mentioned this, is a project like this really worked well, not only because it has a large data production, but it attracted a global workforce. Students in Israel were able to tap in. They may not have access to Keck, but they're able to put all their cycles thinking about this. Okay, so that's a different approach to the old framework of proprietary data. Okay, so I conclude from this. Anyway, that's what led me to do if you look at PTF, it has many things in common with SDSS from that, including the global workforce. Okay, so there are new modes of investigation. There's a traditional mode. It will continue. You will build bigger telescopes. They have value. Grand themes will happen. I think, in my opinion, dark energy grand themes is incredibly heavily over-invested. I would not ask your rector to invest in that field at all. But I will ask him something else. Okay, massive surveys. It's very juicy. It'll go on for a while. Okay. The cost of all these modes has increased dramatically. It's actually faster than GDP. Now, some of you may know, my close friends know that I'm very interested in sort of a business and the economic side of science. So if those of you have this thing, you should really read a paper of mine, which I think is the only paper on the economics of astronomy. Okay, so now let's go into synoptic surveys, which is part of what we are talking of for this theme. Time domain, which we'll hear more. There's a dizzying growth in time domain. Look at these cameras around the world. Hypersuprime camera on Subaru, dark energy camera on Blanco, PTF now taken off, ZTF working as of 10 days ago, just at least in an engineering sense. Pan-STARRS 1 in Halakla, LSST coming up in 2020 in Chile. The total investment of this is maybe, at this point, about $400 million on this slide. Okay, so transient object astronomy, I don't go in detail. This is what I wish I really talked a lot. There are other things, stars being shredded by the nuclear black holes. We may be able to get an entirely new view of most of the black holes, which are actually not active. Okay, we can continue doing what Swift has done, look at the high Z universe with more and more distant GRBs, and we can do new types of cosmography with lens supernovae. I'll touch upon that a little later. Okay, so I think, in my opinion, transient object astronomy, as I said, it's not the start. We're already in it in a very big way. In fact, I even predict that in about 5 years, the game will be over, meaning that it'll be the linear growth. You work hard, you get some papers, you have to work twice as hard. Okay, maybe it's even 3 years from now. And the reason we are not understanding is that these surveys, which have been very successful, but they're all PR-led, meaning there's some group of people with some enthusiastic person like me leading it and say, okay, here's a few things we want to do. There are lots of things these surveys haven't done, unlike SDSS, which is a full menu project. So the project that Israel is Nord I'm leading, in my opinion, it's nothing to do with PTF, IPTF. This I understood. I'm afraid that the rest of my team doesn't fully understand this statement. I view this as ZTF is going to start the era of industrial time domain astronomy. We're not going to scale up with what we have. And LSST in 5 years will fundamentally change how astronomy in optical astronomy is going to be structured. Okay, so let me talk of something which I have been thinking, and I'm sorry, but my thoughts are only, shall I say, rudimentary right now. It'll take another 2 years to fully go through that. Okay, so there are bright star astronomy. There are many investments that are actually happening in what I call as bright star, roughly brighter than about 20th magnitude. Look at this, Gaia, billion euro European missions, fantastic, it's unique, it's amazing. 20th magnitude. Kepler, TESS, 10 to 14th magnitude, but incredibly high precision, 1 part in a million. Atlas ZTF, 20th magnitude, but very high cadence. These are very well tuned to the fact that we can now follow them up. Going fainter is not necessarily better. Just because you have data doesn't mean you know much. In fact, if you have a lot of data, you sometimes, almost always, you know less because you get data poisoned. Okay, so many people mistake data generation with science. Just because there's Google and internet doesn't mean you're any brighter. Some things are easier, but many of us are actually less bright. You go to you're sitting down at a bar, someone asks something, immediately people type in because they no longer can remember very well. So there's an example of that. Okay, so I'll come back to this part later. I would say that there's some very interesting possibilities, especially, I would say, at the departmental levels, especially at places which are not like Caltech. Our style has been very capital intensive. You go and do the state of art, may cost $100 million, may cost more than that. But that's not the only way. So these are examples of LCO-GT, a $50 million project. It has new capabilities, which are very interesting. Rapid response, global network, focus to a cause, OGLE, KMT. And I think these are things that, as a professor, I would like to start thinking about. And I urge all my colleagues to not just think mainstream. These opportunities are very, very interesting. They're only limited by how cleverly you can think of. Of course, in the end, you need money. And this sort of game starts at about $1 million. It's hard for me to imagine anything less than that. Okay, but it can be clever. You can go ahead and reuse existing facilities, which is how PTF was built. The total run-out cost of PTF was maybe $4 million. But the capital investment on what it was built was large. Okay, so let me give some examples of small projects with potential for impact. Okay, so this is RoboA. I won't play the movie. It'll take time from this. It's basically, you may not see, this is a 60-inch telescope. And what you see is a 12-watt JDS uniphase ultraviolet laser. It goes up, it's pulsed. You get Rayleigh scattering from the atmosphere. We form an artificial beacon 10 kilometers up because that's when you run out of air. And we use that artificial star to correct for the atmospheric distortions, fix it up. Of course, adaptive optic systems have been around, but they're far more expensive than this approach. They're better suited for large telescopes, 8 meter, in which case necessarily you have to make your star much higher by roughly that number. And therefore it has to be in the mesosphere, so you're forced to use sodium lasers, which are custom made. No one else in the world other than astronomers use sodium lasers. But JDS uniphase lasers are used by the thousands, maybe hundreds of thousands. Your PC board are drilled by those lasers. We order it, it comes in, put it power, light on, 12 watts come out. Okay? If it fails, you call up the company, they send you another one, you send the old one back, $10,000. That's it. We're in business. Anyway, so this is an incredibly fast AO system, unlike the ones, let's say, on VLT or Keck. Our time to go from source to source is maybe a minute at most. So we've been able to do some unusual kind of very high throughput science. And the total run-out cost of this, meaning from T equals 0 to now, maybe it's $3 million. Okay, maybe 3.5. Okay, another innovative idea which has actually turned out, it was a little bit of a gamble, but worked well. Here's the observatory, Palomar Observatory. Here's where ZTF is located, 200-inch. This is where all of modern time domain astronomy began. It's an 18-inch mid telescope, Bardet and Zwicky. And here's a 60-inch telescope these are all roboticized, by the way, not the 200-inch, but these two. Okay, so with this we have installed a robotic spectrograph that can basically, limited only by when you want to command, you can go from detection to spectra instantly. Unfortunately, it takes some time. So when Avisha was talking about 20 minutes, we can do that. It's very easy to do that. Okay, so data hits the images are made, real-time analysis, machine scoring, high score, observe, okay. And that led to an interesting discovery recently. This is a lens system. It's a Supernova 1A. And what you're seeing here is this ring, which is almost like a perfect Einstein ring, at least to an astronomer. And that's a galaxy. The host galaxy is so aligned with the lensing galaxy, so it's you, lensing galaxy, supernova into the board. Supernova light comes in, is gravitationally lensed, and this is a supernova. It actually has a few more images, but these are on the optical you can see. This immediately allows you, of course, with only one, it's hard to do cosmography, but if you get 20, the precision of this is actually as good as many of these maybe $50 million dark energy BAO missions. Okay. Another one, which is more fun, it's more sort of I can relate to, find a source, get a spectrum, and right away you see that here's our spectrum taken, in this case, not rapidly, but it could have been, and turns out to be just looking at it. It's a tidal reception event, very close. This turns out to be more common. So this is a star being torn apart by its black hole, central black hole. Okay, so next thing I've been thinking of is, okay, this has been so successful, why don't we make a telescope which does only this? That's it. So we're thinking of version 2, we understand how to build this machine for the 84-inch. It's a long story, but the US NSF actually has gifted me an 84-inch telescope. So we can have this completely dedicated. Anyway, so this usual stuff, you run around. When you build these machines, you don't have to be bright at all. I can assure you this. I have the greatest experience in this field. I know exactly how bright I am, which is not much. But if we build a machine, the data writes itself. You just wake up in the morning, look at the data. Okay, let's write another Nature paper. It actually works. Okay, well, so we'll do all that stuff. Okay, but as a professor, the part I like to do is there are many student projects. I think that's, to me, very important. One student can learn to be an instrumentation person. In fact, ACDM version 1, one of your Israeli students was in charge of one of the camera systems. Then another student can become an observer. You say, yeah, here's an 84-inch telescope, run it. You learn a lot. These are complex systems. Third student could go into machine learning, because I'm a radio astronomer. I really don't like staying awake. I never found that interesting. So I want, and I'm also not good at recognizing spectra. So I want machine classification. Spectra comes in, machine classified. So 1A, then I'll say, fantastic, I don't even have to wake up. It's not a 1A, okay, it's interesting with Dovey's classification. It's very interesting, we'll wake up. Otherwise, there's no rush. Okay, so despite my personality, actually people like me, which always surprises me. So the Navy called me up a few months ago. They said, Shri, we like your work. We want to gift you with the astrograph. So it's an amazing camera. This is a 500 megapixel camera with a telescope. So I'm thinking of what to do. It's 28 square degrees, 1 arc second, so we can actually start doing galactic plane explorer. We can choose a spot in the galaxy and stare, and then slowly march along with the seasons. And this is very interesting stellar astronomy that can be done. And we have some ideas from the Ogle project, what sort of things to do. Here's not a project I'm involved, but I like this. Take telephoto lenses, and they have some special properties. They have very low surface scattering. So you can really make very high dynamic range surface brightness imaging. Led by Yale and Toronto, these two professors, the total capital cost is $1 million. These are all commercial Nikon telephoto lenses. And they discovered a whole new type of galaxies. They're very, very diffuse. They're oddballs, and they're not known before. You could look with the brightest, biggest telescope, you won't find them because it requires very low scattering things. So I hope I convinced you that there's some really exciting frontiers here in astronomy. Okay, so the last big topic I want to talk is highly multiplex spectroscopy. So we've been talking a lot in this meeting, and many astronomers tend to talk in terms of time domain to mean take images, see something new come up, or a star go up and down, or a microlensing signal goes up and down. That's fine. It's in some sense, visually easy to understand. But time domain in spectroscopy is a little harder. And it's, I would say, almost a frontier field. The few experiments that have been done have already told us some very interesting new results. Okay. So if I had to start all over again, I'd start with this because it is so new. Okay, so there are worldwide, there's a huge investment in highly multiplex spectroscopy. So I have to explain for those of you who don't understand. The old style spectrum was like you see in those old pictures. There's Newton, there's a prism, sunlight, little rainbow. And for a long time, that was the model we had. The slight improvement that Newton didn't get right, I forget the name of this astronomer, was to put a slit so that the actual image had lines. That's how you see these Fraunhofer lines, okay? And that was a design for almost 400 years or whatever since Newton. So astronomers were taking spectra one object at a time. But now, if you realize the field of view of a telescope, a well-designed telescope can be very large. You get one spectrum. But now, through this multiplex spectroscopy, you can get spectra of many points, up to maybe a few thousand. The first generation were a few hundred, now they're going to a few thousand. And obviously, if you can improve anything in life by 1,000, I assure you again, you don't have to worry about anything. The data will tell you how to write the papers. Therefore, there's a worldwide investment. It started off with 2DF, Sloan, 6DF, Lamos, Rave, Hermes, Foremost, Weave, DESI, PFS. There are a few in the working. There's a reason why astronomers are investing. But all these guys are trying to do, I would say mainly more objects is better. I'm not talking of that. I'm talking of time domain spectroscopy. We'll go and look at the same objects again and again. You can do something as mundane as state changes in active galactic nuclei. It's mundane in the sense it looks not so interesting today, but we haven't done enough, and maybe there's something here. And I refer to a new SDSS paper, already looking very interesting to me. Accreting binary stellar activity, transients old and new. I can't give you very clear examples right now. I've only been thinking about this for about 6 months. But 2 years from now, I think I'll be well prepared. But the other part is radial velocity. It's a fundamental probe of stellar astronomy. When you see two stars, you think that's interesting because you see in Star Wars, Tatooine system, and so on. If I tell you that two stars you can see as only one, but they're going around each other, that requires a radial velocity. Half the stars are in binary systems, and another half of those are in triple, and so on and so forth. And the sun is single star, so we are a little biased in looking at stars. And this is an essential technique. It's a more powerful technique than imaging. Okay, the initial success of using Sloan, it's a project called Swarm. It's been fantastic. They found two white dwarfs. The sum of it initially looked like one was actually very massive and a neutron star. And I was very intrigued. So with my colleague Van Kerkwijk, we worked very hard. And it turns out it is not a neutron star, which would have blown away everything we'd have known. Okay, that's just the first one. Okay, it's a very interesting project. So what I've been thinking is, okay, we're starting ZTF. We'll start the we'll commission in about a month's time, maybe a month and a half. We'll start the survey in January 1. It's a 3-year survey. But it's already a good time to start thinking, what is ZTF phase 2 going to look like? Okay, we can do more time domain. But even Avishai, who's a big supernova fan, I think after 100 supernovae, even he will agree, okay, it's time to do something else. Okay, for me it's 10, but it's okay. So I'm thinking, okay, ZTF phase 2 will end in 2020, December 2021. What's next? Because all these are large projects. You have to start thinking plans, finding money, vision, building up the community. So the new project called AS4, which is after, it's a crazy name, after Sloan Digital Sky Survey 4 is AS4. And it has two components, one is south and north. So I was thinking, why not combine highly time multiplex spectroscopy with time domain photometry? I think this will be a fantastic thing. I can't, again, if Danny asked me yesterday, do you have some ideas? I said, no, I really don't have great ideas, but we had a cocktail, and right after that, I got a new idea. Okay, so this is not very difficult. So as an example, we can do optimized spectroscopy for eclipsing systems. There are billions of there are millions of eclipsing systems, and you can't get all the data if you just did it blindly. But if I know when the phase is, I can just get 2 spectra, I'm done. So this is a very efficient way to do. But anyway, any of you who have an idea, please let me know. It's an interesting thing to start thinking. Okay, so the last topic I want to say is, if you notice, I'm only talking about projects, data generation, but I already told you, it's very seductive, it's very tempting, and for someone like me, that is almost what I like doing. Think of new ideas, launch projects, write a few papers, finish, move on to the next thing, same, repeat that cycle. But that's really not good science. I have to admit that myself. Okay, but it's fun. So you can sometimes be serious or it can be more fun. I've chosen this latter. So, but really, we do this not to collect data, not to go have fun at taxpayers' expense, or at least, okay, not you say publicly anyway. So is to collect data to understand something about our world, our universe. So astronomy is now what I'd call is officially big data science. And I'll tell you how official this is actually, because I've done a lot of thinking about this one. I'm not the only one. There are many, many people thinking about this very topic. And what's happening is there are 2 fields in science, astronomy and biology, which are actually officially big data big data science. Why these 2? Well, because they're phenomenological sciences. These sciences are not reductionist. In physics, you do an experiment because you have a lot of theory, and that experiment guides, then the theory guides you to the experiment. You do that. If it works very well, the theory gets better in the sense it's proven itself, then we push it again. So that's what happens. So in some sense, CERN is, there's a theory, apparently such a good theory, they turned on CERN, spent $20 billion later, turned out to be, the theory was better and it works very well. There are no surprises, well, at least at my level. Okay, yeah, then they said we had this, we had that, and this, it's only this GB and not that, but really, honestly, it's not all that interesting. It will be really interesting if it turned out something that blew your mind away. Your theory is totally wrong, because that's the only time you learn in life is when you make a mistake or when your theory is wrong. You learn nothing when it's all working well. Okay. So physics is not it doesn't have this sort of richness and scale of experiments like astronomy. And biology is very interesting for the exact opposite reason that physics is now a dry subject. Because there is no theory of biology at all. The Earth saw 5 speciations, okay? Why is it that dinos existed one time? Why, if I go out today, I can see not 20, but maybe hundreds of families of butterflies? There's no theory. So these are phenomenological subjects, and you need to collect data, because only when you get that data, maybe with some luck, you'll understand. In this way, astronomy is a little ahead of biology. It's amazing. We went from sort of looking at galaxies and not even knowing what they are, to now telling the universe was born 13.6 billion years ago, and we're getting down to plus minus 1 million, maybe at some point plus minus, okay, I don't know about 100 years, but we're getting there. Think about it. It's pretty amazing, actually. Okay, so what we are now seeing is success. These facilities are highly multiplexed. Everything is multiplexed. If you look at ZTF, we're doing 47 square degrees. The earlier surveys were a few square degrees. And we are reading it faster. So the astronomical data is growing much faster than almost anything else. Okay? Unfortunately, astronomers' productivity is not increasing exponentially. This is a fact. And neither is their pay increasing. It's perhaps even decreasing. I don't know. Okay. So here's some things. See, let me read this. Normally it's a bad idea to read something, but it's interesting. You should understand. So we compared genomics with 3 other major generators of data, big data: astronomy, YouTube, and Twitter. We are up there. We are really up there. Now we are serious business, okay? Astronomy has faced the challenges of big data for 20 years and continues ever more ambitious studies of the universe. Particle physics, we know them. I don't know if there are any particle physicists. They think they're like really great, high-tech, so on. Forget it. They have 0 footprint in this area. They generate very little data. Okay. This is not my statement. This is a well-known paper here. Astronomy, YouTube, and Twitter are expected to show continued dramatic growth in the volume of data to be acquired. Okay, I understand astronomy, but Twitter, in my mind, only twits. Sorry, okay.
It's increased a lot since the last election.
Yeah. Anyway, it's okay. I'm in Israel, so I can make these sorts of jokes. Okay, fine. So anyway, Twitter, who uses Twitter? Of course, the only twits use Twitter, but the content is 0 there. But anyway, apparently they're growing too. Okay, so what is our, so let's stop, let's take a moment and start thinking, what are we doing? Why do we want to build these things? And what's the solution? So I told you, some of us want to build big things. We'll enjoy it, but many times they do something interesting. But our utilization of the data, as an astronomer, I question myself. If you ask me what fraction of PTF we actually used, I haven't done this very quantitatively. My guess is maybe 10%. What fraction of ZTF we'll use? I would say at least the group itself will use maybe 1% or 2%. Okay, so we need to address this actually. And for that, I'll end by talking of someone who's been thinking more about this, and their problems are more pressing. In the sense, astronomers have actually done very, very well for 20 years, as that study showed. But now we are going to enter a regime where we won't do so well. Okay, so there's a goal of the genomic community. It's called the $1,000 Genome Project. The goal of $1,000 Genome Project is to basically sequence your gene for $1,000 so that you can actually come up with personalized medicine. You look at this, you say you have this problem and so on. Okay, you may wonder about the moral side of this, but let's say we'll just look at it as pure scientists. The idea is if I can personalize my medicine, I can take preventive measures, maybe we save a lot of money, other than maybe have a longer life. Okay, but the data production of the genome with our genomes will be stupendous. Okay, so the storage requirements for these genomes is going to be challenging. In fact, it's been well known for a long time that the storage requirements for genomes, if this project took off, would far exceed the rate of Moore's law. But a solution has been found. This is a fairly respectable university, not as good as Caltech, but they do a few things. They claim that thanks to all this increasing data storage, unfortunately by 2025 we'll be no longer the kings of the big data science. It'll be genomics, maybe YouTube, and then astronomy. Okay, so the cost of DNA sequence following, we may be very close to the $1,000 benchmark that's been set. Okay, so the solution for us, I mean, not solution, I think this is what I want to leave this message. The field is very exciting, things are happening, but people like me are the dinosaurs now. Dolby may be the new generation, okay? So the problem in genomics, as in astronomy, is we know how to generate data. We even know how to store it, it seems, but we don't understand the data. Much of the genomics data, even if you get your thing sequenced, you look only for a few specific spots, and that's it, just like we do with our PTF, ZTF data, okay? So I would say, since I see a few young people here, for you, you shouldn't do what I'm doing at all. You should go and start understanding that the real action is in interpreting this data and to develop those skills to actually go and analyze the data. Anyway, so I gave this talk in the sense of the future of astronomy, since this is the future theme. And that's it. Question there.
Yes, so Shri, that was an inspiring talk. Thank you very much. I have a question for you. I mean, when all this hard work in generating data in any given project, what's your view about how that data should be released?
It's inevitable if you look at the internet, right? Look at all the newspapers. I do pay for subscription to New York Times and LA Times, mainly because I want to support them, as otherwise I think they'll go out of business. But the way I read my actual news is through the Google aggregated, news.google.com. I read those, but then I read a few other things. So I think the era of proprietary data for most of these services is over. The data rates are so large that even if you wanted to have a head start, you can't consume that. So I suspect most of these projects will have like a 6-month or 1-year thing, especially in the first couple of years. And after that, they'll decrease it to 6 months and 3 months, and then that's a forget it. So the people who are built should get, in my opinion, a head start and do the few things they have in mind. Otherwise, that would be a bit not very motivating. But I think most of this data will, as the buzzword is, data wants to be free. Yeah.
And the astronomers' salaries are not in step with that, then there'll just be gobs and gobs of data that remain
We're already there. Yeah. We're already there. Okay. So that's my thing is I don't have an immediate solution, but let's look at another field which is a bit ahead on this part, and there's more money involved in genomics than in astronomy. So I'm hoping that will be an example for us to understand, because things will happen much faster in that field. No, I don't think we should have, okay, it'll be more is always better, but I don't think so. I think, I just think we have to understand what is our, we have made a transition from being a data poor field to a data rich field, and now we have to understand what exactly is our goal. And I would say we are in a era of confusion right now.
Actually, I wanted to make a few comments. First, just a statement that, in fact, Tel Aviv University, starting next year, data science will be a compulsory course at the undergrad level for every discipline, because we already realized that this is like multiplication table. Second, about the things that you said in advice. Whoever wants to get into this field should be also in touch with the other disciplines, because data science, basically, by the way, when I asked around the campus how many people work on big data, 10% of the faculty members say they are working on big data. Okay, big is a relative statement, but in fact, all of them share exactly the same problems. The issues of how to collect the data, how to store, how to share, how to analyze. So whoever wants to get into this field should be also in the whole community of the other people who are collecting and analyzing data. And about the rays, in fact, the data is rising exponentially, it's true, but you don't need more astronomers. That's not the point. You need more machine learning. It's not a problem of people. It's a problem of the machines. So you need good ideas, but I don't think you have to exponentially increase neither the salary, of course it's a good idea, but neither the salary, not the number of people, it's actually the technology. And last, I think some people believe that in 10 years, the computational power will be much higher because it's not going to be the classical calculations anymore. And that will be, I believe, a major breakthrough, and this is one of the things we are also planning to invest. Now, this is something that you never know in 10 years whether quantum computing will be here or it will take 50 years, but this will be a huge, huge breakthrough in this field. Thank you.
Okay. If you have any other comments, then thank you again, Shri.